Good afternoon. This is Boaz Heidelberg, and our discussion in this presentation is vector calculus. We will take a look at the rotating system and how we represent position, velocity, and acceleration in this system. And we also move then to two rotating systems and see how the representation is done in a more complex situation. What we see on the screen is a stationary coordinate system, x0 or y0, and a rotating coordinate system, x1, y1. The position at this particular instant of x1 with respect to x0 is theta, the angular velocity is omega, the angular acceleration is alpha, and these are the positive directions according to the right-hand rule. Omega is defined as a vector that has only component in the z direction, and alpha is also having component in the z direction. Alpha is the derivative of omega. Now, here's a point over here which is rotating with the x1, y1 system, but it also has a relative motion with respect to the x1, y1 system. Now, if you like to find the absolute velocity of point P as seen by an observer in the inertial coordinate system, then we define the derivative in absolute term by drp dt, and this equals to the relative velocity of point P with respect to the moving coordinate system plus omega cos rp. Now, the reason why we have this element is imagine that P is not moving with respect to x1, y1, then it will have only a velocity perpendicular to rp in a magnitude of omega cos rp. Why is it cos rp? If you look, for example, at the small displacement of theta of this coordinate system, then this point P will move a small displacement perpendicular to rp, and the magnitude will be d theta times rp. Now, if we take d theta will be in radians, rp whatever units you will have, and if we take the derivative of this small displacement, we will get derivative of theta dt, which is omega. So this is how we get omega cos rp for the effect of the rotation of this moving coordinate system on the velocity of point P. If we now want to move and look at the absolute acceleration of point P, we have to take a derivative once more of this expression. So the first derivative will be rp double dot, and then we're doing it in a relative coordinate system, and then we'll have omega dot cos rp, which we see over here, then plus omega cos rp dot, and this is the third term, and then we have to hit these two guys with another omega cos this expression, so we'll have omega cos rp dot will be here, and then we'll have omega cos rp. And we have 1, 2, 3, 4, 5 terms which we can group together because this term shows up twice, and what we end up with is that the absolute acceleration of point P equals to the relative acceleration of point P with respect to the moving coordinate system plus the tangential acceleration alpha cos rp, and another term which is the centrifugal acceleration omega cos rp, plus the last term is the Coriolis acceleration 2 omega cos rp dot. If we now take a look at a situation where we have more than one moving coordinate system, we have an inertial frame at the base of a robot. We have another frame which is moving with the base of that robot, this element over here. It has x1, y1, and z1, and it has a fixed point A, which is the pivot of the arm, and we attach another coordinate system, which is x2, y2, z2, to that pivot. Now, x1 is rotated with respect to x0 and angle theta, which is the yaw, and x2 is rotated with respect to x1 and another angle, which is theta 2, and that will be the pitch. Now, if you look at the position of a point inside the gripper, the absolute position is defined as RB, and it is equal to RA plus RB with respect to A. This is this vector here. So this is absolute vector, this is absolute vector, relative vector. If you want to look at the velocity of point B, absolute velocity of point B, we'll first have to take the derivative of the RB with respect to the absolute coordinate system equals to the absolute velocity of point RA plus the absolute velocity of RB with respect to A. Now, the absolute velocity of RA is equal to R dot plus omega 1, which is the velocity of coordinate system 1 with respect to 0, cos RA. But since point A is fixed in coordinate system 1, this term will drop out, and all we're left with is this term. If we look at the acceleration of point A, we use the same formulation as we had before, this formulation over here at the bottom, and we get RA double dot plus the tangential acceleration plus centrifugal acceleration plus the Coriolis. And again, because point A is stationary in coordinate system 1, this term and this term will drop out, and all we have is the tangential and the centrifugal for point A as a result of its axis rotation with respect to coordinate system 0. Now, looking at the absolute velocity of B with respect to A, again, we use the same formulation. It will be the relative velocity of B with respect to A in a moving coordinate system plus the absolute velocity of point 2 with respect to the inertial frame. We define it as capital omega 2, and it is equal to the sum of the two relative velocities. 1 omega 1 is the velocity of 1 with respect to 0, and omega 2 is velocity, angular velocity of x is 2 with respect to 1. The sum of the two is the absolute velocity of the coordinate system 2 with respect to coordinate system 0. Now, so that will be the absolute velocity of point B with respect to A. If we differentiate it, we get the absolute acceleration of point B with respect to A. Again, the terms are exactly as we had here, just replacing omega with the absolute velocity of omega 2 and the absolute acceleration of omega 2 for the centrifugal. Absolute acceleration of frame 2 is alpha 1 plus alpha 2, and these are the relative ones. Now, the final absolute acceleration of point B with respect to the inertial frame is the absolute acceleration of point A with respect to the inertial frame plus the absolute acceleration of B with respect to A in the inertial frame. And this is the result. Now, in many cases, we may have to resolve various vectors which are represented in various coordinate systems, either 1, 2, or 0, and we have to resolve them in different coordinate systems. So this shows us just an example of how we may resolve omega 2 And omega 2 we see over here is along this axis, y2, and it is expressed in coordinate system, local coordinate system 2, but we may want to resolve it to the inertial frame, and we want to see the component of omega 2 as they are being reflected on x0, y0, and z0. So to do that, we have to actually take omega 2 as it is resolved in 2, which is this one here, and actually hit it with a matrix of transformation which transforms from 2 to 0. This will give us omega 2 resolved in 0. But to get this matrix, we have to take two matrices, one which transforms from 2 to 1, and hit it with another matrix which rotates it from the resulting vector from 1 to 0. So the multiplication of these two matrices will give us the rotation matrix from 2 to 0. Now, what is the contents of these rotational matrices? We have the rotation from 2 to 1. This is the pitch. We found it earlier. It might have been the transport of what we saw before, where you see that the cosines on the diagonal, this is the axis about which we rotate, and the minus sign in this particular case is on a bottom, and it's the transpose of the matrix which transforms from coordinate 1 to coordinate 2, which we had previously shown. So this is the transpose. And then similarly, similar to what we had before, we have a transformation from coordinate system 1, which is having a yaw angle with respect to 0. This is the terms, again, cosine on the diagonal. We rotate in about z, so it's 1, zeros on a column, on a row, and the minus sign is up here, similar to what we see in previous presentations. If we take these two matrices and substitute them in this equation, we will get actually a resultant matrix, a little bit more complex. We multiply times omega 2 as shown in coordinate system 2, and we'll end up with a component in coordinate system 0. It happens that the component of omega 2 along the x0 will be minus omega 2 times sine theta 1, and it will have a y component omega 2 times cosine theta 1, and it will not have any component in a z direction. Now you could visualize this by assuming that this coordinate over here is rotated theta 1, so x0 will be here, y0 will be here. This will be the direction of y2 is parallel to y1, so if y1 will be here, y2 also will be heading in the same direction. And if you look at omega 2, which will be in that direction, then the resolution of it along the x0 line will be this times the sine of theta, and it will have a negative component. Now, similarly, if you look at that omega 2 and resolve it along y0, you see that it will be omega 2 times cosine of theta 1, which will be a vector omega 2 here, drop a perpendicular to y0, and it will be omega 2 times cosine theta 1. This concludes our presentation for vector calculus, as we will see in upcoming exercises. Thank you.